Everyone, sections 3.1 and 3.2, pairs of lines and angles and parallel lines and transversals. Example 1. Think of each segment in the figure as part of a line. Which line or lines or plane or planes appear to fit the description? All right. Line or lines parallel to GH, which is right here, that contain point F. So they have to be parallel to GH, but they also have to contain point F. So CD is parallel to GH, but it doesn't contain point F. So the only answer here is line EF. Lines skew to GH. So again, here's GH. Skew to GH and again containing point F. So again, line AE is skewed to GH. Line AD is skewed to GH, but neither of those contain point F. The only one that is skewed to GH and containing point F is line BF. Line or lines perpendicular to GH that contain point F. So again, DH is perpendicular to GH, but doesn't contain point F. CG is perpendicular to GH, but doesn't contain point F. EH is perpendicular to GH, but doesn't contain point F. The only one that does is line FG. Plane or planes parallel to plane GHD. So plane GHD is the right side of this prism. So the only plane that is parallel to that plane is the plane on the left side of the prism, ABF or AFB or AFE, any of those. So plane ABF. That was example 1. Example 2. Classify each pair of lines as intersecting, parallel, or skew. So AB, which is here, and EJ, which is here, parallel. AB and FK, parallel. AB and ID, they are not in the same plane. They'll never intersect, skew. EF is here. IH is here. They are in the plane of the front face. They're not parallel. They're coplanar, so they must be intersecting. Not on the page, but eventually they would intersect. EF and NM, EF and NM, they are not in the same plane. There is no plane that contains them. They're not parallel because there's no plane that contains them. The second they're non-coplanar, they must be skew. CN, which is here, and FG, which is here. Again, there is no one plane that will contain them, therefore they must be skew. Okay. Complete each statement with the word always, sometimes, or never. Two skew lines are always, sometimes, or never parallel. They are never parallel. Skew lines are non-coplanar, parallel lines are coplanar. Can't have the same, they can't have them be both. Two parallel lines are always, sometimes, or never coplanar. Well, I just answered that question. They are always coplanar. A line in the plane of the ceiling and a line in the plane of the floor are sometimes parallel. Sometimes they're skew. And how can I show you that? Let's take a look at this picture. AB is in the plane of the ceiling. GH is in the plane of the floor. AB and GH are parallel. AB is in the plane of the ceiling. FG is in the plane of the floor. AB and FG are skew. Sometimes they're parallel, sometimes they're skew. Part D, two lines in the plane of the floor are never skew because they are coplanar. So they can't be skew. Two lines that are not coplanar always, sometimes, or never intersect. Two lines that are not coplanar must be skew, and they never intersect. Part F, two lines skew to a third line are always, sometimes, or never skew to each other. Okay. Two lines skew to a third line. DH is skewed to EF. CG is skewed to EF. DH and CG are parallel. They're not skewed to each other, but EF and DH are skew. EF and BC are skew. DH and BC are skew. Sometimes they are skew to each other. Sometimes they're not. They could even be intersecting. So two lines skew to a third line are sometimes skew to each other. Two lines perpendicular to a third line are always, sometimes, or never perpendicular to each other. So this doesn't say that they're coplanar. If they are coplanar, DH and CG are both perpendicular to GH. So they are coplanar. DH and CG would be parallel. But it doesn't say that they're coplanar. DH is perpendicular to GH. FG is perpendicular to GH. DH and FG are skew. DH and GH are perpendicular. EH and GH are perpendicular. DH and EH are perpendicular. So, two lines perpendicular to the third line are sometimes perpendicular to each other. Two lines parallel to the same lines are always, sometimes, or never parallel to each other. AB is parallel to CD, GH is parallel to CD, AB and GH are parallel. AB is parallel to CD, EF is parallel to CD, AB and EF are parallel. Two lines parallel to the same lines are always parallel to each other. Two lines parallel to the same plane, this is a little different wording, are always, sometimes, or never parallel to each other. EF is parallel to the plane of the ceiling ABC. GH is parallel to the plane ABC. EF is parallel to GH. EF is parallel to the plane ABC. FG is parallel to the plane ABC. EF and FG are intersecting. In fact, they're perpendicular. So the answer here is sometimes. If a line is parallel to a plane containing the line is always, sometimes, or parallel, always, sometimes, or never parallel to the given plane. So if a line is parallel to a plane, so EF is parallel to plane ABC, a plane containing the line, EFG contains EF, is always, sometimes, or never parallel to the given plane. EFG is parallel to ABC, but EF is parallel to ABC. ABF contains line EF, and ABF is not parallel to the ceiling ABC. So the answer here again, sometimes. Part K. Two lines parallel to the same plane are always, sometimes, or never parallel to each other. So EF is parallel to ABC, GH is parallel to ABC, EF is parallel to GH. But EF is parallel to ABC, GF is parallel to ABC, EF and GF are not parallel to each other. Sometimes. Okay, slide this up a little bit. Two lines perpendicular to a third line must be parallel. If it said two coplanar lines, then the answer would be true. DH is perpendicular to GH, CG is perpendicular to GH, DH is parallel to CG because they're all coplanar. But DH is perpendicular to GH, EH is perpendicular to GH, DH and EH are perpendicular to each other. DH is perpendicular to GH, FG is perpendicular to GH, DH and FG are skewed to each other. So the answer actually is sometimes they're parallel, not must be parallel. So this is false. It's a similar question that was asked up here. In a plane, so now we have in a plane, two lines perpendicular to the third line must be parallel. I just showed you that example. That is true. I used DH, CG, and GH as an example. That was example 4. Example 5. Classify each pair of angles as alternate interior, same side interior, alternate exterior, or corresponding angles. Okay. So EBA and FCB, the transversal is AD. They're both in the upper left-hand intersection of that transversal. They are corresponding angles. Part B, DCH, DCH, CBJ, CBJ. So again, the transversal would be BD here. DCH, CBJ are both in the bottom right-hand part of that intersection. Again, they're corresponding angles. FCB, FCB, and CBL, CBL. This is one of my favorites. Types of pairs. And I'm tracing it out lightly because I'm going to erase it in a second. Because they make a Z-like shape. When you look at the two angles, they make a Z-like shape. And the pair of angles that always make a Z-like shape are alternate interior angles. So they are alt-int angles. Let me erase that. Okay. So you want to look for that Z-like shape for alternate interior angles. FCL, FCL, and CBJ, CBJ. FCL are here, and CBJ are here. Ah, sorry. I read this one from up above. FCL, FCL, and BLC, BLC. And let me trace these. FCL and CLB make a C-like shape. I know it's backwards, but it's still a C-like shape. And the pair of angles that make C-like shapes are same side interiors, or as our book calls them, consecutive angles. So, or consecutive angles. I'm not going to write that up because I don't have enough space. Let me erase that. Tracing. So part D, same side interior angles or consecutive angles. I will use those names interchangeably as we go on. HCB, HCB, and CBJ, CBJ, they again are making the C-like shape. I know it's turned upside down, but it's still C-like. This is same side, interior angles, or consecutive interior angles. Part F, G, C, H, and G, L, J. The transversal is GL. GCH is in the upper right. GLJ is in the upper right. These are corresponding angles. ABE right here. CLJ is here. So ABE, CLJ. A little bit harder to see. The transversal is EJ. They are outside of the lines that are being cut, and they are on opposite sides of the transversal, making them alternate exterior angles. That was example 5. Example 6. Find the values of x and y. So let's take a look at the value of x first. These lines here are parallel. X is corresponding to this angle here. This angle here forms a linear pair with the 120. So this must be 60 degrees. Again, these lines here are parallel. X and the 3y plus 6 form corresponding angles. So they have to be congruent if the lines are parallel, which they are. So 3y plus 6 equals 60. 3y equals 54. Y equals 18. Part B. There's a few different ways we can do this. I'm going to go for the x first. I could go for the y. Actually, the order doesn't matter. If I take this 110, this is a vertical angle with 110. So it's also 110 degrees. X and the 30 plus the 110, so this angle here, coupled with the angle x, form that C-like shape. They are consecutive interior angles or same side interior angles. They must be supplementary. So 110 plus 30 is 140, plus x is 180, so x is 40 degrees. X and y are corresponding angles, so y is 40 degrees. Another way to get that, this is 30, so this is 30. 110, the 30, and the y add up to be 180. So again, 110 plus 30 is 40, plus another 40 is 40. That's 180. Part C. So we have parallel lines here and here. We have parallel lines here and here. We have the alt-int angles making the Z-like shape here, making these 65 degrees. We have the Z-like shape here, making the X and the 65 alt-int angles again. So X must be 65 degrees. Y corresponds to the 40 and the 65, so here and here correspond to each other. The transversal is right here. They're both in the upper right hand quadrant. So 65 plus 40 is 105, so Y is 105 degrees. So that is example 6, part C. Example 7. We have line KL parallel to line L. That's what's given to us. I put that in the diagram here. We have a whole bunch of different angles, 8 different numbered angles. And our goal is to prove that angle 6 is supplementary to angle 7. And we're just filling in the blanks here. So our first blank, first reason, is given. Almost always the case that it's going to be given. Angle 6 and angle 8 have the same measure. Angle 6 and angle 8 are here and here. They are corresponding angles of parallel lines. So they are equal in measure, they're congruent, and that's going to be the corresponding angles theorem. Angles 7 and 8 add up to be 180 degrees. Angles 7 and 8 are here and here. It's a linear pair postulate. I know on the answer key it says angle addition postulate. That's because our previous book where I got this proof from used angle addition postulate instead of a linear pair postulate. It's just a different setup for the other book. Our book defines it this way. It uses linear pair postulate to answer this type of a problem. Example 4, instead of writing angle 8, we're going to replace it with angle 6 because angle 6 and angle 8 have the same measure. Substitution property. And because the measure of angle 6 plus the measure of angle 7 equals 180, then 6 is supplementary to 7. Definition of supplementary angles. QED, quad erit demonstratum. That which I wanted to demonstrate has been demonstrated. Okay. Example 8. We're going to use the diagram from example 7, this one here, to write the proof. So we still have line K parallel to line L, but this time our goal is to prove angle 2 is congruent to angle 7. So I'm actually going to do that up here because I have the space. Statements, reasons. You see that? Yep. I think if I do this, I can have the diagram as well. Okay. Statement 1. Again, I can do this. You guys can't. Right in the squigglies. Instead of rewriting the given, when you get your college degree, then you can write squigglies. Until then, rewrite the given. Statement 2. So, because these lines are parallel, angle 5 and angle 7 correspond to each other. Corresponding angles of parallel lines must be congruent. Angle 5 congruent to angle 7. Corresponding angles there. Okay. Take a look at angles 2 and 5 here. Angles 2 and 5 are vertical angles. Angle 2 congruent to angle 5. Vertical angles theorem, VAT. 4. Angle 7 is congruent to angle 5. Angle 5 is congruent to angle 2. Angle 2 congruent to angle 7. Transitive property. Congruence. And that's what our goal was. Angle 2 congruent to angle 7. Q, E, D. Quad erit demonstratum. That which I wanted to demonstrate has been demonstrated. Okay. Example 9. Again, we're going to use a diagram from example 7. We're going to write a proof. K is still parallel to L, but this time we're going to prove that angle 1 is supplementary to angle 7. That's our goal, is to prove angle 1 is supplementary to angle 7. I'm going to try and fit it in here, although this one's a little bit longer. I'm going to try writing smaller. Statements, reasons. Statement 1, again, squigglies because I can. You can't. Statement 2. I got to find a pair of angles that are supplementary to eventually get angle 1 supplementary to angle 7. So what pair of angles do I know that are supplementary? Well, 5 and 8 form consecutive angles or same side interior angles. They're supplementary, but neither 5 nor 8 are part of the angles 1 or 7. I mean, they're related to them. But let's go with angle 1 and angle 4, because they already have angle 1 in there. So angle 1 is supplementary to angle 4. How do I know that? I know about by the consecutive interior angles there. Here. Sometimes called the same side interior angles there. Okay. At this point, are we giving something else? No, I'm just noticing a typo on the answer key. So, what can you tell me about angles 4 and 7? Well, actually, let me back up before that. What does this tell me? If angle 1 and angle 4 are supplementary, then measure of angle 1 plus the measure of angle 4 equals 180 degrees. How do I know that? Definition of supplementary angles. Now, angle 4 and angle 7. Measure of angle 4 equals the measure of angle 7. How do I know that? Vertical angles theorem, VAT. Okay. Instead of writing angle 4 here, I can write angle 7. Can replace it with angle 7. Measure of angle 1 plus the measure of angle 7 equals 180. Substitution property. And final statement, statement 6. Angle 1 is supplementary to angle 7. Definition of supplementary angles. Q, E, D. Quad erat demonstratum. Finished. So that was example 9. Example 10 is not simple. It's a tricky little problem here. It's definitely a good honors question for us. We have these 3 parallel lines, and we've got a whole bunch of angles in here. And what we're going to end up needing to do, because we're trying to find the values of x and y, is we're going to set up a system of equations here. 120 and 2x plus y form our C-like shape. Our C-like shape means that they are consecutive angles or same-side interior angles, and they must be supplementary. So, what equation can we write? 2x plus y plus 120 equals 180. And if I just simplify that a little bit, 2x plus y equals 60 when I subtract the 120 from both sides. Now, I can do the exact same thing here. I have another pair of consecutive interior angles, or same side interior angles. I can write another equation, 2x minus y plus 140 equals 180. Subtract 140, 2x minus y equals 40. Now I have 2 equations with 2 unknowns. Takes us back to our Algebra 1 days when we have to solve this system of equations. We'll pick one of these variables in one of these equations to solve for. I'm going to use substitution. Linear combination would actually be better here, but I'm not sure if your Algebra 1 teacher showed you linear combination. Your Algebra 2 teacher definitely will. So I'm going to use substitution instead because I know you've been shown that. So I'm going to subtract 2x from both sides here and get y alone. So I now have y equals 60 minus 2x. Substitute in place of this y, I'm going to replace it with 60 minus 2x. Now I have 2x minus 60 minus 2x. Notice I've put this into parentheses to be careful because I'm going to need to distribute that negative sign through. 2x minus 60 plus 2x equals 40. 4x equals 100. X equals 25. And I have found half of the variables. Once I got 25 for x over here, I plug that in here. Y equals 60 minus 2 times 25. Y equals 60 minus 50. Y equals 10. And there is the solution for example 10. Example 11, we're writing a proof. Can I fit it? I'm going to have to fit it on the back side here. So I'm going to be bouncing back and forth between the diagram and the proof. So I'm going to be flipping over back and forth here and there. So we set up our columns here. Statements. Reasons. 1. Squiggly, squiggly. 1. Given. And again, I can do that. You can't. Let's go back to the proof. Segment AS is parallel to segment BT. I've put the arrows in here for you. Normally I won't. Angle 4 and angle 5 have the same measure. Let me mark that. Angle 4 and angle 5 have the same measure. Our goal is to prove that ray SA here bisects angle BSR. So if we do a little backwards thinking, backwards solving the problem, to start with what it is I'm trying to prove and say to myself, well, what must I have shown just prior to this? If I want to say ray SA bisects angle BSR, I had to have said just before that statement, angle 1 is congruent to angle 2. That's the only way I would get ray SA bisecting angle BSR, because that's the definition of an angle bisector, is that angle 1 be congruent to angle 2. So my goal here is to prove that angle 1 is congruent to angle 2. Okay, using our parallel lines, angle 4 and angle 1 correspond to each other. So angle 4 and angle 1 are corresponding angles of parallel lines. They have to be congruent to each other. So, 2. Measure of angle 1 equals the measure of angle 4. Corresponding angles here. Let's show a postulate because our previous book, it was a postulate. Okay. Well, we can see in our diagram, angle 4 is equal and measured to angle 5. Angle 4 is equal and measured to angle 1. Angle 1 and angle 5 have to be equal in measure. So, statement 3. Measure of angle 1 equals the measure of angle 5. Substitution. Property of equality. If you wrote transitive property of equality, that's not wrong. I prefer substitution for measures of equal angles. I prefer transitive for congruent angles. So transitive I like for congruent, substitution I like for equals. But if our book does not differentiate between the two. So if you said transitive property of equality, as long as you put the of equality, you're fine. Okay, statement 4 is coming next. So we go back to our diagram here. What else can we see? Well, we still have this line parallel to this line, and I see a Z-like shape here. Here's my Z-like shape. In my Z-like shape means that I have alternate interior angles. If I have alternate interior angles, then I have congruent angles if the lines are parallel, which they are. So angle 2 is congruent to angle 5. Measure of angle 2 equals the measure of angle 5. Alt, int, angles there. Now that I have angle 2 congruent to angle 5, or the measure of angle 2 is equal to the measure of angle. So angle 1 is equal to the measure of angle 5. Angle 5 is equal to the measure of angle 2. This next statement's pretty easy. Measure of angle 1 equals the measure of angle 2. Substitution property. What did I say in the beginning? My goal was to get angle 1 congruent to angle 2 so that I could say ray SA bisects angle BSR. Definition of angle bisector. QED. Finished. All right, example 12. This is by far my favorite historical example in geometry. So about 220 BCE, Eratosthenes, that's probably not an actual picture of Eratosthenes, but it's one that I found on the internet, estimated the circumference of the Earth. He achieved this remarkable feat by using 2 locations in Egypt. He used Syene and Alexandria, and yes, this is the Alexandria in Egypt, where the Library of Alexandria was. Syene now has a new name. I don't remember the name of the new city. It's not called Syene anymore. But he assumed that the Earth was a sphere, which is pretty close, it's not exactly, and that the sun's rays are parallel. And again, pretty close. They're not exactly parallel, but they were close enough for his measurement. He used the measures of angles 1 and 2 in his estimation. Okay, we're going to see later on this year how he actually came up with the calculation for the circumference of the Earth, how incredibly simple it was. He only needed to know 2 measurements. He measured this angle here and he measured this distance here from Alexandria to Syene, and he was able to come up with a pretty accurate estimation for the circumference of the Earth, accurate to within 100 miles. So we're going to classify angles 1 and 2 as alternate interiors, same side interiors, or corresponding angles. So angles 1 and 2 make the Z-like shape again. So they are alt-int angles. And how did Eratosthenes know that angle 1 was congruent to angle 2? He knew that because he knows, or he knew, the alt-int angles here. And again, we will revisit this problem in the future, and we will see what his calculation gave us, and we'll compare it to a modern calculation and see how close he was. He was very close. Okay, so that was section 3.1 and 3.2. Thank you very much. Bye.